I'm MC Toon, the worst rapper in the world, and tonight I've got a flat Earth pilot on. And give me just a second here. I will bring him in and we can have a little introduction. And here we go. He goes by Knowledge. How are you, Knowledge?
Hello, people.
Got a play in there. All right. Yeah, go ahead. Introduce yourself.
Well, people do call me Knowledge because when it comes to learning, there's no ledge. But my real name is Quincy Carr. And to tell you the truth, Mike, I've been an activist for a long time. Like I've been involved like in politics like for a while. I was a part of Occupy Wall Street. And so, you know, I've been awake. I've always been like, since 2006, 2007, after my accident. You probably don't know, but I'm probably one of the only people that fly, and I'm actually paralyzed. So I fly with like, you know, hand controls, and I got about.
So how do you do rudder?
Yeah, I got a bar that sits in my lap, and so the bar goes left to right, and so then I control the pedals like this. So in 2016, Captain Sully gave me an award to be a.
Is he the one that landed in the river there?
Right.
Yeah.
Exactly. So Captain Sully gave me an award to be a flight instructor. So I went to school, and I've been doing it now for about 4 years now. I used to fly for the news. I used to fly aerial Titan signs, and now I'm a flight instructor, sir.
So a friend of mine did, because people were wondering, a friend of mine who's a pilot did verify with the FAA that you are, because people are wondering, you are single engine certified instrument and
yes.
Certified. Is there a certification for a instructor, right?
Yes, exactly. Yes.
Okay. So, well, it is an unusual thing for a pilot to think that the Earth is flat. So, do you would you like to just go over a little bit what your thoughts are on that? Okay.
When again, I've been awake for a long time, right? You know, you go down and you find out all about these, you know, the truths and the new world order and the elite, and then someone says to you flat Earth, and you're like, no. When someone told me about the Earth being flat, I said, no, I'm a pilot. I know the Earth isn't flat, right? Someone said, they told me have I seen the curve, right? I said, yeah, I've seen the curve. Mike, the next day I went flying and looked for the curve and didn't see it. So, in me becoming an instructor, I revamped everything that I thought I learned about flying and relearned it from day one of ground school, day one of flight training. Your son will tell you, day one, right? The day one of flight is you must keep the wings level, okay? Now, when something is level, Mike, the word level means flat. Your assignment is to keep the wings level. If something is level, it's even, it's flat. You keep the wings level with the horizon. Now, if something is horizontal, again, it's flat. So day one of flying is all about trying to keep things level and straight, and you're flying a line with the horizon. Never are you flying a straight line over a ball.
So a quick question. Is this flat?
I mean, is this flat?
Yeah, it's a is it flat?
Well, it's flat, but
Okay.
you're holding it at an angle.
Yeah, is it level?
No.
Okay, so flat and level are not the same thing.
Is it flat? Yeah. When you're trying to fly, though, you're trying to be flat. Like that right there is not the way that a plane flies. A plane doesn't fly like that.
So yeah, so what would you say to a person if their wings were like this and you didn't want them like this? You would say fly it.
I would say
it's
turn
still
the wings
flat. Yeah, it's still flat, but you need to be level. Right. Yeah.
Right. But now, if you're level with the horizontal, with the horizon is still flat. So I would say turn my wings to get level, and therefore I'm still horizontal and I'm still flat.
Okay. So when you looked to see if the horizon was curved,
yes.
So you came into that with a hypothesis. The hypothesis being something like, well, if the Earth is spherical, then there should be a certain amount of curve, and it's relative to my elevation. And
because
right,
I just told some guy the other day, nah, bro, it's a ball. You're an idiot.
So all right, but for the hypothesis, right?
Okay.
Did you then now? So being a pilot, you have a good deal of geometry that you need to be able to handle. That maybe people that don't do piloty things aren't going to handle as much, right?
Right, sir.
So I do for my work. I do a good amount of math, not a ton, but more recently I've gotten back into more of the math and more of the geometry that I learned when I was in university. I studied electrical engineering and computer science, so tons and tons of math there. But writing business software, which is what I do professionally, I don't do as much math. So a lot of people don't do math day to day, and so they would have trouble with geometry. If I said, "Can you solve a triangle?" a lot of people would not know what to do, right?
The way that I explain flat Earth, it's so easy because I'm an instructor, so I try to make students learn it in a way so that it makes sense, because not everybody can do all the math, but maybe if we just use our science and use what we can observe, we can see for ourselves that there's no way the world could be a ball spinning 1,000 miles an hour as opposed to a flat plane.
Okay. So back to the hypothesis, right? So
okay.
So from a plane, and you're in a single engine plane, so you're at 5,000 feet. All right. So at 5,000 feet, hypothesis, at 5,000 feet, I should be able to see X curve in the horizon, and you do the math for that, and then you would somehow measure to see if you could identify that much curve. Did you do that? How much curve should you see at 5,000 feet? How many degrees of arc should you see?
Well, again, the fact that I didn't see a curve and it looked flat to me, I said, okay, what I'm seeing is it looks flat. Like I'm looking at it being flat, and the fact is that inside of the airplane, right, there's an instrument called an artificial horizon, right?
Yep.
In every single airplane, it's always flat. So this one instrument is flat irregardless of how high you are. That's why they say the horizon is always rising, because it always rises to your eye level.
I have certainly heard that claim. All right, so back to the hypothesis.
Okay.
At 5,000 feet elevation, how much left to right curve should you see?
I should see some.
How much?
And, well, people say that they've seen a curve from a beach. So I'm like, well, if they see a curve from a beach, I should see some curve from 5,000 feet. Some curve. I see no curve.
Okay, so it sounds like you didn't actually do a hypothesis and calculate the ramifications of that hypothesis.
I looked at what I could see, and I didn't see a curve, and I kept trying to look for it, and then I asked other pilots, have they seen a curve? They all say, yeah, bro, I've seen a curve, but they haven't.
Okay, so, the problem I'm seeing with that particular experiment is that you don't actually know how much curve you should be able to see because you didn't calculate how much, right? So to do that, you would get your distance to the horizon, and then you would find out what percentage of the circle, and you'd find out how much of the arc, right? There'd be some geometry to that.
Well, supposedly the Earth curves at what? Was it 8 inches per square mile, right?
No.
So at 8 inches per square.
That's
isn't that the Earth supposedly?
That's what flat earthers say. It's completely wrong.
Okay.
That started with Samuel Rowbotham in the 1800s, and it's not true. So
here's the problem that I have is that if we talk about the math on the curve, and we don't talk about where's the curve, like just show me the curve, like irregardless of where it is, irregardless of how high it is, where is it?
Yeah.
Well, 10,000 feet, 20,000 feet.
Well,
every single picture that I've seen, it's flat. They got balloon footage to 120,000 feet. It's flat. So where's this curve, whether it be at 5,000 feet or 10,000 feet, where is it? I haven't seen it.
All right. So I think there's a little flaw in how you constructed your hypothesis there, because you didn't actually construct. So at 5,000 feet, the amount of curve that you would see is very small. And I don't think that the human eye can necessarily measure that small amount of curve. Right?
So when would I see the curve? And why
So at what elevation could a human eye see curve for sure? Somewhere.
Pilots tell me all the time they've seen it.
Yeah, you said that.
Yeah, and so I tell them to show me pictures, and they don't have any.
Yeah.
So then I try to go to Google and find pictures of this curve. I don't seem to see it.
All right. So if you did see the curve of the horizon, you would change your mind? Of
course. Science is observation. If I can't observe it, I can't even test it. I gotta observe it first.
Okay.
So I went up and looked and said, oh wow, it's flat. Wow. Okay. Well, that's what I can see.
All right. So I'm going to show you. There's a flat earther named Dwayne Kellum, and I'm going to show here a little bit of analysis of a video that he did. Are you seeing what I'm sending there?
Okay.
Okay. So this is on my website, mctoon.net/Dwayne Kellum. I'll zoom in a little bit here. So he has a balloon called High Altitude Balloon 24 I See Stars. And in that video, he sent up a Sony camera, which is actually the same camera, same type of camera that I'm using. It's an A7S II, which is a better camera than I have. And the lens is a Sony FE 50mm 1.8 aperture lens. All right, so that particular lens is not a fisheye lens. It has very, very small introduced distortion. And there's a website, there's a lot of websites that rate lenses and analyze the amount of distortion that they add. And this one in particular, thedigitalpicture.com reviewed it and shows this grid here. Do you see this grid? This grid shows the amount of introduced curve or distortion that the lens adds. Now, it doesn't add any visible distortion. So this lens is a non-fisheye lens, and it's called a rectilinear lens because it doesn't add significant distortion. So anything you see in it that's straight is going to be straight in reality, and anything you see in it that's curved is curved in reality. Okay, and you can examine this yourself. You can look at the analysis of the lens yourself too on my website. So here is from that video a still from that video. And it's at 117,000 feet. And I'll zoom in on it here. And what I did is I drew a line across it here. And on the left side, zoom it way in so we can see. On the left side, I put the top of this yellow line just next to the horizon. You see that?
Right.
On the right side, I put the top of the line right next to the horizon. Right next to it. It has an inset of a GoPro lens there.
Okay.
And then in the middle, you can see the horizon is curved up from that yellow line.
I mean, I'm saying, where's the curve still? To me, it's still
right here.
Looks flat.
That's actually curved. So right here, the top of the yellow line is right next to the horizon. But on the right side, hold on. On the right side, the top of the yellow line is right next to the horizon. And in the middle, the horizon has curved up from that yellow line. And then, now you said just a minute ago, if you saw the curve, that you'd believe it. So now here is that very same picture. And what I've done is I have just done a left to right compression, and you can see very clearly the curve there. And when you do a horizontal compression, it doesn't introduce curve. Straight things remain straight, and curved things remain curved, but they're easier to see.
That's not what I see every day. Every day when I'm doing
now hold on a second. This is not 5,000 feet. This is 117,000 feet, much higher than you ever have been in your single engine plane. Much higher than many people have been in any plane ever, right? This is a flat earther too that did it. You can download the entire raw video and you can look at every frame you want on your own.
Okay. So I would want to address the fact that the maps that we use to fly with are all flat.
The maps. All right. So hold on a second. That's a different topic. Do you want to admit that there's curve and move to a different topic?
No, I don't want, because this is not what I see every day. Of course, every day.
Because you're only at 5,000 feet. You're not at 117,000 feet.
But they've got balloon footage.
This is footage from a balloon
that shows it flat at 120,000 feet.
Yeah.
There's
maybe, just maybe, that particular video you were looking at was fisheye, and you looked at a still from a particular or a part of the video where it was curved from the lens. But this video, this particular one, this is a rectilinear lens, and I showed you we have the exact details of the lens here. Now remember, I asked if I showed you curve, you would believe it, and now here you are.
But that's not a curve. That's not curve. I mean,
how's that not a curve?
How do you curve water?
Well, I'm sorry. How is this not a curve?
But I'm saying, how would you curve water?
That's a different topic. That's a different topic.
No, because if the Earth's a ball, you must be able to curve water.
Absolutely. And so this shows that water does indeed curve.
That's why they call water sea level. And then whenever you're like flying, it's called a flight level.
Yeah, but here's the problem.
Your
Level,
level.
but level doesn't mean flat. We already established that. And when we're
Level
talking
does
about
mean flat.
but when we're
Keep it
talking
level.
when we're talking about the shape of the earth, the definition for the adjective for level referring to the shape of the earth would be the one that you want to refer to. For example, from the late 1700s, leveling is the art of ascertaining the perpendicular ascent or descent of one place above or below a horizontal line of another for various intentions, and of making out courses for conveyance of water. The true level is a curve conforming to the surface of the earth as ABG. Now, this is from a surveying manual from the late 1700s. So level, since at least the late 1700s, when referring to the shape of the earth, means curved. So when you say level means flat, you do not have any evidence to support that in the dictionary definition, because when we look at the dictionary definition for level pertaining to the shape of the earth, it means curved. Now, this isn't one. I have about 45 definitions here on this website.
When I try to teach them to like land and I say look out and keep the plane level, they know what that means. Inside your body is the vestibular system, which tells you if you're pitching or banking or rolling. Like, our bodies were just designed to be.
Yes, yeah, we can determine the downward vector.
You know, I mean,
that's it. So that doesn't have anything to do with level. Downward vector, if the earth is a sphere, downward vector would be towards the center. And if the earth is flat, then downward vector would be straight down.
The world spinning. No one feels the world spinning because
what part of your what part of your anatomy feels constant velocity?
Again, you don't feel constant, but you only feel acceleration.
Oh, all right. And how much, for your hypothesis, how much acceleration should we feel? How much acceleration should we feel at the equator?
Well, again, someone tell me, because they're saying it's accelerating.
I can tell you.
I'm saying it's not.
I could tell you how much acceleration we expect to see at the equator, but you seem to have already determined your answer without having done the actual analysis. So,
man, listen, the sun and the moon are 28 miles away. Okay, the sun and the moon.
28 miles away.
28 miles away, Mike.
Oh, okay. My goodness, that's new.
Right now, how do you know this? Because of shadows. Okay, shadows only come from close light sources. Okay.
Okay. Well, hold on a second. Your audio stopped. Hold on. Your audio cut out.
All
right, there. Yeah. Say what you said before.
What'd you hear?
You talked about shadows.
Okay. The sun and moon being 28 miles away, and you can test this because of light sources and close shadows. No matter where you have a shadow, you always have a source of light that you can see. Your eyes can see 50 miles. 28 is within the 50.
Wait.
There's no way your eyes can see 94 million miles. You gotta let go of space.
Why can we only see 50 miles?
Because the atmosphere, and I guess they've done the science though. They've done the science. Like your eyes can see about. I mean, even when like I'm. Even when like I'm like.
Well, I've never seen anybody actually claim that you can only see a certain distance.
Well, you couldn't have an object that's so far away, but you can still see it.
Why?
How is something so far away, but I can still see it? there's no way that a sun could be so far away, but you can still see it.
But you've said that several times, but do you have any
Right.
supporting evidence for that, or is it just a claim?
Because I can see the sun, and it rises in the east and sets in the west, right? East to west are not straight lines. East to west are not straight lines. East to west go in a circle. Okay.
But are you suggesting that the light from the sun travels in a circle in order to get to us, or does it travel mostly straight to get to us?
The light travels downwards and it moves at 15 degrees every hour.
No. The sun, yes, the sun does. But when the sun is sending its light towards us, like shortly after sunrise, does the light from the sun travel mostly straight to us, or does it somehow curve as it's traveling to us?
It travels straight to us.
Okay, so if the sun is if the Earth is a disk, right, then on sunrise on the equinox on the equator, let's say, we should see it rising 45 degrees north of due east, right?
Every day the sun is in the east and it goes to the west. Again, make it simple so people can like.
I don't. I'm sorry. It doesn't need to be simple. We can do deep analysis of this. I've finished 8th grade math. We can apply 8th grade math to this at least. Right?
The sun is moving and you can test it and you can see it. That's how we have time zones, because the sun moves at 1,000 miles an hour every hour. From here to New York is a 3-hour time zone because the sun has moved from the east at 1,000 miles an hour. You got to have it simple because not everybody can do the math. So,
but you and I can, right? We can. That's fine. The people that can't handle the math, we can let them just trust us. But let's do the math on this.
From here to New York is about 3,000 miles, right? And the sun moves at about 1,000 miles an hour.
Okay.
15 degrees every hour, or 15 times 24 would be 360. And a disk has what? 360. All the airplane's flight instruments, right? You've seen the flat Earth model, right? Every airplane instrument that we use for navigation is all based on that. Degrees in a circle, from the heading indicator to the RMI, the VOR. As a pilot, we fly degrees in a circle because we live on a circle.
So, all right. Well, let's do this. Let's do this.
Okay.
I got the flat Earth map. Is this the map you kind of like?
Yeah.
Okay. So the North Pole in the middle there. So here's the equator, and here's somebody on the equator, and let's say it's the day of the equinox, right? So on the equinox, the sun travels around the equator. Right?
You mean the summer solstice?
No, the equinox, twice a year.
Yeah. The summer solstice and the winter solstice.
The solstices would be when the sun is over the Tropic of Capricorn or Tropic of Cancer. So I'm talking specifically about the equinox.
Well, on the summer solstice, that's the longest day of the year.
Yeah, no, but my question is about the equinox.
Okay.
So not about the solstice. So on the equinox, I just want to be sure that I understand your model here. The sun travels around over the equator mostly.
It makes a spiral every six months.
Okay, on the day, I'm just talking about the one day of the equinox.
Okay.
I'm just looking to see a yes or no. Does the sun travel over the equator on that day?
The sun's track is the equator.
Okay, so on that day, we agree The sun is above the equator. So if this observer here,
that track, the sun and the moon that you have, that is the equator.
yeah, that's what I said.
Okay.
So on the sun is visible on that day for 12 hours, and it's dark for 12 hours on that day. So this, for an observer down here on this part of the Earth, on the equinox, the sun is about here when it appears to rise for them, right?
But the sun is never rising or setting.
Yeah, but there is a time of the day when you cannot see the sun, correct?
Right. So
okay, so 6 hours before midday, the sun appears on the horizon. It crosses the horizon. It would be about in this location when that happens, correct?
Oh, okay.
Okay, and then at noon, local solar noon, the sun is directly overhead.
That's why it's
Correct.
so bright, because at noon it's right.
Okay,
it's actually
just yes or no, just yes or no on this. All right, and then 6 hours later, when the sun appears to set, the sun's going to be about here, right? So it's traveled half of the circumference of the equator on that day while it was visible for this person, and then the rest of the day it's up here and not visible for those people, correct?
Right.
Okay. So now at sunrise for this person, when the sun first appears to rise, this angle here we can do. This is simple geometry. We can just draw a line here, right? And so we've got east right here. So due east is that line there, right?
Okay.
Right. So that's due east. And then this is due north. So this sun would appear about 45 degrees north of due east.
Okay. Okay. So the sun looks like it's rising and setting, but the sun stays the same height. It's called.
I wasn't talking about that. I was just talking about the horizontal angle to the sun. So this is a top-down view of a flat Earth idea here, right? So the sun, if the sun is here, as you agreed, if the sun is here, then at the moment that the sun appears to the observer there, it must be 45 degrees north of due east, right? Or your bearing, right? Because bearing 0 is due north. This would be bearing 45, and east is bearing 90.
Okay, that's not what, again, that's not what we see.
I understand I understand very well that's not what we see, but that's what your model predicts. Unless I'm misunderstanding something, you could explain how your model predicts it differently.
Okay, the way that I see the model is, nature doesn't move in a straight line, right? It's always a spiral. So from my point of view, maybe I'm in it alone, but I feel that the Earth makes a spiral every six months. 6 months, it spins closer to the center and slower. So because it's closer and slower, the days are longer.
Okay, but I was not talking about different days. I was talking specifically about one day. Just about one day at one moment when
the time, it controls the
that doesn't change anything.
Seasons.
According to your model, how can we predict the angle of the sun when it's first visible to an observer on the equator on that one day of the equinox?
What's important, Mike, is that we know the sun moves. That's what we do know.
I think this is vitally important, because I can predict using the globe the angle of sunrise. You should be able to predict using flat Earth the angle of sunrise.
You can't tell me any motion or movement. I can tell you that the sun moves, but just watching it. Watch the birds fly. Watch movement. You know when something moves, Mike. You know when something moves.
Sure, and we have detailed instruments that can measure movement, right? Like in a commercial airplane, there before you can even take off, you need to allow the IRU to identify the latitude, right? Are you familiar with that? That's not typically in a smaller single engine plane, but are you familiar with the IRU determining
like FMS like type systems on a certain
a larger commercial plane has an inertial reference unit, and before you take off, you need to allow it to. It takes a few minutes, 6 to 10 minutes, depending on a few different things, for it to measure the latitude, and it does that in a certain specific way. How does it do that?
Well, here's one, right? The fact that airplanes fly lines in the sky, right? How do you draw a line over a sphere?
Lines can be curved.
Go look behind you at those charts right there, right?
Whoa. Lines can be curved. A line is not straight.
Lines cannot be curved. A line over a sphere is an arc. Game over. It's game over. Because we make a flight plan. We draw a line.
So
you can't have a line
just a second
over a ball.
Here's an equation for a line. Yeah, do you see that?
Show me math. Show me experiments, man. Experiments.
Okay. This is you're talking about the nature of a line. This is an equation for a line. Y equals mx plus b. This is taught to kids all the time in elementary school and in middle school. Y equals mx plus b. That's the formula for a line.
You drew that on a flat piece of paper.
No. Come on. What's the shape of this line?
I don't know.
Okay.
I don't know.
That's a curved. It's a curved line.
That you use a flat piece of paper to just draw on in general, like.
Yeah, that's
true.
Map,
but the map behind you is flat.
Yeah, but just a second. Every single one of those maps has 3 words on it. 3 words on it. Lambert conformal conic. Do you know what that means?
I don't know what that means.
Okay, then I would really not be happy about. Oh my gosh. Because when you chart. When you use a chart to go from one, hold on, let me finish here. When you pull out a paper chart, because sometimes you need to pull out a paper chart to go between places, right? And certainly 20 years ago, you weren't using an iPad to put your routes in. Hey, you use that chart. On that chart, every single one of those charts that you would use that have paper and that you would draw lines on, every single one of them has Lambert conformal conic on it.
You're drawing a line.
What does Lambert conformal conic mean?
You're drawing a line still.
I'm asking a very specific question, and you're kind of avoiding the answer. What does Lambert conformal conic mean?
Mike.
It is critically important. Because if it didn't say that, if it had some other thing in it, then Lambert conformal conic, it would drastically change how you would have to draw the lines and get the distances between things. But now here's the thing. I have a friend who would like to come in, who is a pilot, and who can maybe talk to this a little more than I can. Would you be okay with that? I'll back off. I won't involve myself anymore if you're okay with that.
Go for it.
Okay. All right. His name he goes by Wolfie6020.
Oh, I've heard this guy. I've heard him before. He's there to always criticize anybody who's yeah, I know about this guy
Yeah.
before.
So he's
I know I've heard before.
It's a guy, not her, but
he's not there to learn. He's just there to like bash. But hey, you know what though? Here's the thing about flying though, Mike, is a good pilot is always learning. You're always learning.
Yeah.
You're always learning, right? So a lot of pilots have this big like ego that because I've been flying so long. Oh, I know the Earth's a ball. You can't learn something if you think you already know it.
Okay. Well, I mean, I'm always open for more information. But I haven't really, I got to be honest, I haven't seen anything that's been very convincing.
I mean, just the fact that, okay, we live on a globe, like there's global leaders, like there's a global system, Mike. I'm sure you can see that, right? I mean, even on like the idea of the politics, man, it's globalism. I'm sure you at least
I don't know what that really doesn't have anything to do with the shape of the Earth. It has more to do about.
It does. Oh yes, it does. Because the same people that are behind this are the same people that gave you this globe model. How would they have as much control as they did if nobody believed that there was even a globe? You can't have globalism without the globe
I think
idea.
People might just call it internationalism, I suppose. I mean, the name isn't really all that important.
Well, the model is important because.
Wait, and how long have you been flying?
20 years.
20 years. You got your private license 20 years ago?
Yeah.
Okay.
I was like 19.
All right. All right. I did send it to Wolfie, and he says he hasn't seen the email yet, but it's been sent. So
has he seen the curve? Because every pilot
you can ask. Yeah, you can ask him.
Because Mike, every pilot that I talk to, they tell me that they've seen the curve. Now, I know last month I met a pilot, right, that flies. You know what the U-2 spy plane is?
Yes. Yeah.
Okay. He said that, but between 70,000 and 80,000. There are so many weather balloons up there that he has to dodge around them. So I'm thinking to myself, why are there so much like are those what we're using for actual satellites?
I don't know how that has anything to do with it. So like bicycles exist, therefore
Right.
Motorcycles don't? I don't think so.
Okay.
Right. Just because a high altitude balloon exists doesn't mean that something else doesn't exist.
Well, then too, I'm sure you know about space and NASA. Hey, Mike, I know an astronaut, right? Right? He's a good friend of mine, right? He's an astronaut, but he didn't go to space. He never went to space.
Well, so he wasn't an astronaut.
Well, my point being is that
So wait. You know an astronaut, but he didn't go to space, therefore he's not an astronaut. So you don't know an astronaut.
That's my point is that I've known this guy for years, right? For years, right? Now that I become a so-called flat earther, now I know why.
So
I know why he didn't go to space.
He trained to be an astronaut, but he's not. Okay, so there's a lot of people that enter the training but don't get there, right? So
you know, National Academy of Space actors, man. Star Trek, Star Wars, space.
Let me say, I met this guy right here.
Okay.
That's Charlie Duke. I met him in person.
Okay.
He didn't just train to be an astronaut. He actually is an astronaut. He actually did go to space.
Or so he told you that.
Well, I guess you can just claim that he's a liar, I guess, with no evidence.
Well,
which would be
many
common thing.
Again, many astronauts have been caught. I'm sure you know. I'm sure you've seen it, Mike. You've seen it.
Caught. They've been caught.
They've been caught with green screens, harnesses.
No, they've not. That's silliness.
Green.
Send along the actual stuff. But here's the deal. The Earth's shape can be measured because it's a physical thing. We can just go measure it. So, do you have any measurements?
Measurements.
Like measurements of flatness or measurements of stationariness.
I don't feel it moving.
Okay.
Therefore, it's not.
But you don't have a part of your anatomy that feels constant motion.
But again, whoever said that the Earth was spinning must have felt acceleration, which
but you already determined that you did not calculate the expected amount of acceleration that you would feel. You don't know how much you should feel. And which way would that acceleration be?
Even go exactly. So
which way?
I don't feel it.
Which way would the acceleration that you feel be? Which direction?
Well, if the Earth is spinning east, right, then I should feel it west.
No,
right?
you should feel it.
That's weird though.
You should feel it up.
But
up. It's called centrifugal force.
Okay.
A centrifugal force is well understood. If you take something and spin it, there's a force, and it's dependent on the radius and the linear velocity. So, it's away from the center. So on the Earth, the centrifugal force is up. Now, how much should it be? You didn't do the calculations. So you don't even know, you can't even answer the question of I should feel it because you don't know how much you should feel it.
Though? I mean,
you can't even answer the question because you didn't do the math.
Motion.
But listen,
math is not science and experimentation.
That math is part of it, right? So you form a hypothesis. Your hypothesis that you're trying to
observe movement.
Just listen up. Your hypothesis that you tried to put together is that I should feel the acceleration. How much should you feel? I can answer that question. The amount of acceleration you should feel on the equator is upwards 0.03 meters per second squared. That's how much you should feel.
So what does that feel like, Mike?
0.03 meters per second squared is not very much, but we can measure.
Thank you.
We can measure it, and it has been measured. And here's the cool thing. At the equator, the downward acceleration is modified by this upward acceleration. And so the normal 9.8 meters per second squared, which is about how much downward acceleration is all over the Earth. On the equator, it's slightly less. It's 9.79, 9.78 meters per second squared. So we can measure, so we can have the hypothesis there should be less downward acceleration. We test it, there is less downward acceleration. Now, this information.
In a vacuum, Mike.
I'm sorry. Do you just change topics whenever you don't have an answer to something? That seems a little disingenuous. Could we just finish one topic and you just say, "I'm sorry, I can't address that any farther. Let's go to a different topic."
Because I mean, there's so much proof. There's so much proof that we live on a flat world as opposed to a spinning ball.
Well, there's actually zero. There's actually zero because you said we would feel it, but you don't know how much you would feel.
But
so your hypothesis is worthless. let me tell you this. Knowledge, your hypothesis, you didn't even form a hypothesis. You said we should feel it, but you don't know what direction you should feel it, and you don't know
But
the
I don't
quantity.
feel any direction.
But do you have the ability to feel 0.03 meters per second squared? Nobody does.
Right.
You lack the ability. You lack the ability to feel that much acceleration. So you say, I should feel the acceleration, but you can't actually feel that quantity of. So you should not feel acceleration.
Right.
That's the answer. Exactly. Which matches exactly what the model is for the globe.
Maybe it's just not spinning because we all feel
that is an alternative hypothesis. And then you need to explain.
We say, damn, oh my gosh, the world.
But now here's the deal. You now have the explanation that you need to provide for why is there less acceleration on the equator.
What?
The floor is yours. Why is there 0.03 meters per second squared less acceleration on the equator if the Earth is not rotating?
That proves that we live on some ball flying in space on 1,000 miles an hour.
Don't change the topic. Don't change the topic. You now have the onus to explain why there is a lower acceleration on the equator. Go ahead.
Because we live on a spinning ball, Mike.
Well, I would accept that. That does make sense. But
that makes no sense.
Being that it's flat.
No sense, Mike. I mean, again, I've been figuring this whole thing out. Like,
but you didn't actually do.
Space.
You said, hold on, no. Let me review this. You said we should feel acceleration, but you had no idea what that actually meant. And you didn't know the direction. You didn't even know the direction.
I don't need to know direction. I need to observe some direction.
You absolutely do need to know. You do need to know the direction because you said I should feel it.
The movement. Now, when I look at the sun actually moves. It goes from the east and west. Now, and that you can look at and you can see it. You can calculate it because the Earth is a timepiece, and the sun shows you what time it is.
I've heard people say it before, but it doesn't actually support your case. It's just words. Do you have any measurements of the Earth being stationary? Measurements. And any measurements of it?
If I go Bible is
I don't know. Bible, that's just a claim. That's just a claim.
Okay. Because the problem that I have though is the idea of space. Space cannot exist.
I was asking for measurements of stationariness.
Well, I mean, because
I can accept that you don't have any measurements of stationariness. Just say that. Say you don't have any. That would be the honest thing to do instead of changing the topic when you got cornered because you don't have anything to support your case. Just
I know I don't feel it spinning.
Honest.
I mean, I know that.
Yeah, we already determined that you should not feel it spin.
Right. So I can't observe any direction if I don't feel any motion forward.
So the only way that you know of how to measure rotation is your own feelings. Now, in an airplane, in an airplane, do you only use your own feelings?
In an airplane, do I only use my own? No, I use science. I use observation.
Okay, so where are your measurements of non-rotation then?
Because I don't feel it rotating.
Okay, but we don't expect it. We don't expect you to feel, right? Fly a plane in a hard. Hold on. Listen to this. Fly a plane in a hard bank and then feel your way out of it. You can't do that. You have to use the instruments, right?
Hold on, wait a minute.
What's that?
Mike?
Yep. I'm here. You still there? Something happened.
Yep. We're back.
All right. So people, I have sent the link to Wolfie, but it's not getting through or something. So I'll send another one with a little more content.
Here's the problem though, Mike, is that people cannot, the flat earth model does not conform to space. So
the flat earth model doesn't conform to anything, dude.
Well, see, most people believe in space. So
yeah, but you already couldn't, your model already couldn't predict the angle of sunrise. It failed. It completely failed by 45 degrees, not a small amount. It's 45 degrees off for the angle of sunrise. Right?
Right.
But I can tell you, I can use a globe and I can tell you the angle of sunrise for any position on the globe for any day in the future.
Okay, Mike, show me space in a vacuum.
Show me space. What the hell does that mean? Show me space in a vacuum.
Side vacuum.
What the hell even is that? Show me space in a vacuum?
Yeah, like I'm sorry, space. Thrust in a vacuum.
Thrust in a vacuum?
Thrust, combustion. Yeah, thrust in a vacuum.
Okay, are you familiar with the laws of motion? Can you maybe just name the laws of motion, or name one of them? Just one of the laws of motion.
Sorry, you cut out Mike.
So can you name one of the laws of motion? I'll just
let's go for every action. There's an equal and opposite of reaction.
There you go. So
right.
that's how rockets work in a low pressure environment.
Cars use their tires to push off the ground. Fair?
I'm sorry. You I don't care. No, I don't care to hear your misunderstanding of it.
Hold on.
You asked a specific question. I gave a specific answer. Your lack of understanding is not a disproof.
Wait a minute, Mike. Wait a minute. Cars use their tires to push off the ground. Planes use their props or jets to push off air. Boats use their props to push off of water.
And neither of those are rockets.
But if you're in space, what are you pushing off of?
Nothing.
What are you reacting off of?
You quoted the law of motion. You quoted the law of motion that is responsible for rockets working in a vacuum.
But they don't. But thrust does not work in a vacuum. There's no air to push off in a.
It doesn't need air. You explained it.
What do you mean you don't need air? Yeah, you need air, Mike.
Because a rocket shoots backwards the particles in the combustion chamber.
Air.
No, not against the surrounding air.
Yeah.
Look, your misunderstanding of science is not a debunk of science. All right? Your inability to understand your inability to grasp science is not a valid argument against it.
You cannot have thrust, propulsion, or combustion in a vacuum.
Why would you think?
That's why NASA fakes it. National Academy of Space Actors. They're astronaut.
What the? Are you unaware that rockets bring their own oxidizer? Is this new information for you? Did you get to this age of adultness and not know that rockets carry their own oxidizer with them?
Elon Musk just got caught with a mouse on space.
Okay,
CRS
listen up.
He's busted.
You change the topic whenever you get cornered. You got cornered again. Do you realize? No, listen up here. Do you realize that rockets bring their own oxidizer with them?
And they push off against what?
You got cornered again and change the topic. Answer this question without deflecting. Do you realize that rockets bring their own oxidizer with them? Don't deflect.
They do.
Okay,
yes,
so they can combust in space. Thank you very much. You also noted the second or the first law of motion. Every action has an equal and opposite reaction. So when a gas combusts in the combustion chamber of the rocket and it forces it out the back, that is thrust for the rocket forward. But no air is involved.
Thrusting against
nothing. Every
because
action has an equal and opposite reaction. You said that.
Reacting off of
the chamber, the combustion chamber. It's pressing on the combustion chamber.
And so down here we see that, and so we see all these rockets that come up and curve over right in the ocean. They curve
you
over
got cornered and changed the topic again.
But Mike,
you got cornered and changed the topic every time. I've got your tell.
On,
you change the topic every time you get screwed. You're just repeating. Parroting things that you heard on YouTube. You don't understand the science. The science is beyond you.
Why have they censored they've even censored YouTube? Why?
Okay, change the topic when you get cornered. Again.
Why?
Again, you change the topic when you get cornered. So you can't give a measurement of stationariness. You don't know the direction that you should feel the motion, right? You can say the Newton's law, but you don't understand its implication.
You cannot react off of in a vacuum, Mike.
You absolutely can, and nobody that understands physics agrees with you.
They've flown drones inside.
Are you cornered? Cornered, change the topic?
Telling you.
Because a drone isn't a rocket.
But they've tried to fly drones inside of the vacuum. They don't fly.
A drone is not a rocket. Change the topic when you get cornered. You don't understand the science, therefore it's not true. Sorry, you don't understand the science. Not my fault. Okay, try to understand the actual science. Because
I know
you said every action has an equal and opposite reaction. When a rocket sends a gas particle fast out the back end, the equal and opposite reaction is thrust on the other direction.
But you have to react off of something.
There is off
the ground.
Where is that?
The boat reacts off of water.
Those are not rocket engines.
Where's the fluid?
Your inability to grasp science is not a valid argument against it. You don't understand it. That's the problem. And your YouTube Flurf masters told you these lies and you got fooled. They fooled you. You didn't have the proper education. You didn't have the background in science to understand these things. And you got fooled.
I learned when I was a kid, the Earth's a ball and it spins 1,000 miles an hour because of gravity. I learned about gravity.
Well, then you had a terrible education because that's not why it spins.
Gravity. It's all gravity.
So, gravity is an important part of our universe. It's one of the four fundamental forces.
Gravity is what makes small.
You muted yourself.
Believe in space. There is no space. You gotta let go of space.
So you have said, but never provided evidence for.
Because NASA's faking it.
So you have said, and never provided evidence for.
NASA, Elon Musk, the dude from Amazon. Who's that guy from Amazon?
Bezos.
What's his name? Yes,
Jeff Bezos.
They're all in on it. They're all in on it.
So and you have said without evidence. That's all that you have is claims without evidence. It's pretty sad that you can't back up any of your claims. All you know is that you heard it from your Flurf masters on YouTube, but you don't actually know.
I've seen it myself. They're on harnesses. They're on greens. They use hair gel for the
So,
girl's hair to be
so
like
you have
this.
said without evidence. That's all you have.
Has removed all of those clips that we see are all gone now.
They're actually all still there.
No, there was way more truth that used to be on YouTube. Now we're on Odyssey. Odyssey now? We're on BitChute. Those of us that really know, Mike, we really know.
Yeah, you don't really know, actually, because you don't have any measurements. Where's the measurements of flatness? Do you have any?
I mean, I can measure distances.
No, flatness.
When I do like a flight
plan. So you think that the surface of water is flat. Where are the measurements of the flatness of the surface of water?
Well, why do we call water sea level?
No. There you got cornered and deflected. You know that you don't have any measurements.
Well, why is every ocean even? Every ocean is always
here comes the claim without evidence. Where are your measurements of flatness? You're just saying it, but where are the measurements? Because I can show you measurements that the surface of water is curved.
Don't show me any math numbers. Show me a real curve because to me, I'll show you it's really flat.
I already made you a liar by showing you the curving curving surface. Yeah, I made you a liar. I asked you if you would accept measurements, or if I showed you curve. You said yes. I showed you curve. You said it's not curve. I made you a liar. I mean, you made yourself a liar. This is the image right here that made you a liar. You chose to lie instead of to say that that's a curve.
We don't even know what that is. I mean, what is that? I mean,
that's the curve of the horizon.
No.
You asked to see the curve of the horizon. I showed it to you. Then you said that's not a curve. You lied. You have a religion. That it's flat. Your religion is that it's flat because I'm showing you right now on screen.
The majority always has it wrong.
No,
Mike.
No. I'm showing you.
You're a part of that.
I'm showing you. I'm showing you on screen. I'm showing you on screen the curve that you are refusing to accept is a curve. Don't you see the problem with that? Doesn't that bother you? That you said that you would accept the curve, and then I show you the curve.
No,
and then
show me a real curve. Like this is not what I see.
I don't care that this isn't what I don't care that this isn't what you see. You asked me to show you the curve. I showed you the curve. You said it's not a curve. You lied. That's it. You lied. And you know what they say? You gotta lie to flurf. It's a religion founded on lies. I'm showing you the curve right now that you said you would accept, and you are rejecting it because it violates your religion.
Listen. I used to be
I don't care what you used to be. I care that you became a liar when you became a flat earther, because this is a curve. This is a curve. And you talked about the Bible earlier, which suggests to me that you might think that the Bible's important. One of the 10 commandments is don't lie, but this is a curve right now, and you're saying it doesn't curve. That's a curve.
But, I mean, I know in the word, it says that he sits upon the great
I don't care.
Of the earth.
It's a lie. This is a curve. You don't care about not lying. You are fine with lying. Your religion isn't Christianity. Your religion is contrary. Your religion is opposite the Bible, because this is a curve. You said it's not a curve. That's a lie.
I mean, does the earth curve?
It absolutely does. I'm showing you a picture of it right now.
Is this the only photo from you?
No, that's not the only. This is one. I only needed one to show that you're a liar.
Okay.
Right there. What is this? Is this a curve? Yes or no?
I mean, you're showing a curve, but again, this looks distorted. Like this does not look like.
Yeah, you got cornered, and you're making up excuses instead of just saying, that's a curve. That's a curve. just say that's a curve.
We live on a ball, like for real.
Like
for real.
There are measurements that we're on a ball.
We're on a ball spinning.
Yeah.
Okay.
Yeah, there's measurements. And you admitted you don't have any measurements of flatness, and you don't have any measurements of stationariness.
I mean, I told you, when I look at it, it looks flat.
Oh,
when I feel it, it feels.
But your eyes are not a precision measuring instrument. And being a pilot, would you ever say that I'm only going to fly based on how I feel? Would you do that? You'd lose your license if you refuse to use the instruments. You're an instrument rated pilot. So you use your instruments. You use the instruments. So
shows me how flat I am. Yeah, right. It shows me where I'm level.
Level is not flat. I already showed you the definition.
Horizontal is flat. Yes.
That is the lie that you keep repeating as your mantra in your religion of flat earthism.
Hold the plane even. Don't pitch up.
Hold it level. Yeah, level is conforming to the curve of the surface of the earth. You say it's flat, but it's not. That's not the definition. So, Wolfie, I keep sending you emails. I'm sorry that you can't get them. People are saying to bring Wolfie in. I've sent you dozens of emails. They don't come through. So I sent you from my Gmail account.
You know why? Because all he does is bash, though. All he's gonna do is bash me. He's not gonna try out to learn anything. Like me.
You're not trying to learn. You are trying. You are just denying actual information because you don't like it.
No, that's not true at all. I mean, there's way more evidence of the Earth being a flat plane than the Earth being a ball.
But you didn't present any, actually. So, all right.
Okay.
Wolfie is here. He is working on getting his audio set up. So give me a second here. So he's still working on it. I don't think he'd used Zoom before.
There was a pilot. I forget her name, but she was flying for somewhere over in Europe, and she came out and spoke out against the Earth being flat. And
hello, MC Toon.
Hello, Wolfie.
You've got me now. Okay, sorry about all that fuss, but it looks like I've got audio now. I don't have video because I'm using a large monitor, so there's no camera on this one.
All right. Well, Wolfie, here is knowledge.
Hi, Knowledge. My name is Rob. You can call me Rob or you can call me Wolfie. What would you like me to address you as?
I think he's working on his.
Hear me?
I think he's working on his connection there. There he is.
Okay. Hello.
Hello.
But yes, my name is Rob. You can call me Rob or you can call me Wolfie. I don't mind either way. What would you like me to address you as?
You can address me as Quincy.
Okay, Quincy, good to meet you. Now, I'm not here to bash you. I'm not here to insult you. I'm not here to belittle you. Just, I think it would be quite interesting to the audience to see two pilots actually discussing aviation matters.
Right.
Everything I've heard so far is basically the same old standard flat earth arguments, and there's nothing really directly related to aviation content that a professional pilot would know. So how about we just talk about aviation for a brief period of time, and you can just answer the questions. Yeah.
Sure. I have a question because I'm sure you're probably a more experienced pilot, but you would agree a good pilot is you're always going to learn, right?
Absolutely, a good pilot always learns. I learn every single time I fly.
Right. I know, right?
Let me finish. If you're going to ask me a question, you let me finish. You do not interrupt. Do you understand? I will not interrupt you. I will
Okay,
not
yeah.
interrupt you. When I ask you a question, I will give you all the time you need to answer. So please respect that and do the same with me. Yes, a pilot absolutely is learning all the time. A good pilot never stops learning. I learn every single time I go to the aircraft, every time I power up, every time I fly with a new pilot. Absolutely, my answer is yes, a good pilot is always learning.
Have you ever seen this curve that people say that they see, especially because I've talked to a lot of pilots, right? Almost one of them says that they've seen this curve. I don't agree, but I'm asking you: have you seen the curve of the globe Earth, sir?
Yes, I have, Quincy. I have seen the curve. I fly a corporate aircraft that can operate up to 51,000 feet. I showed a video on my channel just a few days ago, actually at that altitude. I have shown over the years numerous videos and photos from high altitude where you can see the curve. I've actually linked to one of those photos several times in this chat. I'm not sure if you have seen it. I have absolutely seen the curve. Now, can I ask you a question?
Yes.
Okay. They tell me you're a flight instructor. Is that correct?
Yes.
So you are familiar with the VOR?
Yes.
Maybe you could give a 30-second explanation to the audience of what it does and how it works.
I'm so glad, right? Because this is why this is where the flat Earth symbol has to do with superimposing on our flight instruments, because the Earth is a circle. So as pilots, we fly degrees in a circle. There's a instrument that we use called a VOR, which means very high frequency omnidirectional range, or it pretty much allows a plane to navigate on 360 degrees coming out of a circle.
Okay, that's fine. It's a line of sight.
Right. Line of sight instrument.
Yes. What is the range for the VOR?
The range? I think the high class is like 200 miles.
200 at what altitude?
I want to say 40,000 feet.
Okay. I'm looking at a document now that states the range of a VOR. You can look this up on the FAA or general Google search. The range of the VOR below 5,000 feet is 60 nautical miles. The range at 5,000 feet to 10,000 feet is 90 nautical miles. At 10,000 feet to 15,000 feet, it is 120 nautical miles. At 15,000 feet to 20,000 feet, it is 150 nautical miles. It is increasing as the altitude of the aircraft is increasing. It is a line of sight instrument. So can you explain why the range is increasing?
Well, can I explain why the range is increasing? Because as you go higher, is there more radio reception? I mean, as you go higher, is it a better signal?
Okay, it's a line of sight instrument. That means a mountain or the earth or the ocean would block the signal. Do you agree with that?
Yes.
Okay, so if you're at 5,000 feet, you have less range than if you're at 20,000 feet. Do you agree with that?
Yes.
Okay, so what is blocking the signal at 5,000 feet? What causes the lower range at 5,000 feet versus flying at 20,000 feet? If the VOR is located on an island and there is nothing in all directions except ocean.
Because there's a slant range. So the higher you are, you're more at a higher angle of a slant, and so therefore, because you're a higher, you're getting a better signal. That doesn't necessarily mean that you're flying a curve though. Again, it's line of sight.
You're talking about slant range. You're talking about slant range. I'm asking you, what is blocking the distance? What is blocking the range of the VOR signal at the lower altitudes?
What is blocking it?
Because I say the Earth is blocking it. If you look at the Earth curve and you look at the range and you look at the that's what I say. And it certainly fits. If you compare those ranges to those altitudes, it fits beautifully with the geometry of the Earth. So that's what I say it is. What do you say it is on a flat Earth?
I say it's what's blocking it. I would just say the higher you are, you're just getting better signals. Like you're not actually there's nothing that's being blocked. You're just getting better service because you're being higher up. So you're above the ground, and it's less interference from on the ground.
Okay, I accept that as your answer. Now, how about, have you ever used a cell phone in an aircraft?
No.
Okay.
I can't. Well,
okay, all right. I will share my experience, and I'm sure other people have the same experience. On the ground, you get beautiful reception. As you go higher, you lose cell phone reception. Why is that?
Okay.
That contradicts your theory.
Say again?
Okay, a cell phone on the ground, I get great reception. When I take off and I climb through 2,000 to 3,000 feet, I generally lose reception, even though I'm flying directly over cell towers that are just beneath me. So it's contradicting what you explained about the VOR.
Okay, well, Wolfie, you've seen the flat Earth model, right? That we use.
I've seen several flat Earth models. Some flat earthers agree with one, some disagree with it. What is your particular model? Do you support?
Mine's is just the basic one. Yeah, the AE one. Now.
Okay, fine. Yes, I have seen it.
Do you find it kind of like for me, every like the VOR, the RMI, like all the navigational instruments, if you superimpose it, it fits right on that circle. Like, do you see why a pilot like myself looks at the Earth being a circle? Then I look at at our flight instruments that are circles, and that makes sense. Like, or here's one, flying IFR, right? When you fly in IFR flight plan, you draw a line. How do you have a line over a sphere?
Yeah, we'll get to that, and I certainly look forward to talking about flight planning with you. How do you draw a line over a sphere? Grab a beach ball, grab a marker pen, and draw.
No, Wolfie.
That's a line over a sphere.
No, Wolfie. I'm going to grab a flight chart because that's what I do, and my flight chart is flat.
We will get to flight planning. I'm very happy to discuss flight planning with you.
But why grab a ball when we don't fly with balls? Grab a map.
Because you asked me how to draw a straight line on a sphere, and I told you how to draw a straight line on a sphere. If you ask me how we want to do a flight plan, we will get to that. But your question was, how do we draw a straight line on a sphere? Do you disagree that a beach ball or a basketball is a sphere?
No.
That is a sphere. You agree. Do you agree that if I get a marker pen and I draw a line on that sphere, I'm drawing a line on a sphere, correct?
Yes.
That was your question. I've answered it. Okay.
But what I'm saying is that when I teach students to draw flight plans, I show them a map, and the map is flat, and I
Yes,
say draw a line.
Okay, so why did you ask me to draw a line on a sphere?
Well, why did you ask me to draw a line on the ball? I'm telling you, how do we make flight plans if the maps that we use to fly with are flat and there are lines over them? IFR flight plans are lines.
We will get to flight planning. Trust me. We will get to flight planning. We'll get to flight planning. I want to just cover some more of the basics because I don't think we've really finished the VOR question. I said that a cell phone has great range on the ground. It works fine, good reception. As you go higher, you lose that reception. Your argument with the VOR is that the improved range is due to the altitude, the slant range. So the experience with a cell phone contradicts what you're claiming with the VOR. So I'm asking you again. I'm asking you again. Do you think anything is blocking the signal from the VOR? Why does the range increase progressively as the altitude of the aircraft is increased?
You would cut out, sir. Say again.
Okay, it's okay. Look, I'm happy to let that VOR question go if you want to move on to something else.
I want to talk about the vestibular system.
Oh, fabulous, because that was next on my list. What is the sensitivity of the vestibular system?
I don't know.
You don't know. You haven't done an aviation medicine course?
Well, I don't know what the sensitivity. Again, I don't know.
Are you an IFR pilot?
Yes, I am.
Did you not learn the sensitivity of the vestibular system during your training?
I just didn't. Again, we're always trying to learn, right? So
okay,
if I don't know, you can't.
Okay. I'm just saying that because from my personal training and also from teaching instrument flying to students, that is one of the most basic foundations of understanding why we trust our instruments. It is because we cannot trust our vestibular system. The sensitivity of the vestibular system is an acceleration of about 2 to 3 degrees per second. Okay, you can look that up. You can look that up if you don't believe me. But basically, what that means is very slight movement in the aircraft, lower than that rate of acceleration, cannot be detected by the vestibular system.
Okay.
Would you agree with that?
Yes.
Okay, thank you. And that is why pilots can become disoriented in cloud. You agree with that? You're familiar with the graveyard spiral? Yes. Okay.
Yeah.
Okay. So do you agree that instrument pilots are taught to not trust their vestibular system?
Absolutely.
Thank you. Okay.
Now,
so please go ahead.
Okay. Well, my point was when I look at the artificial horizon, and I look at the fact that it's a three-axis gyro, and our vestibular system is also three axes. We know where pitch is, we know where roll is, bank, and a yaw. There's no way the world could be spinning 1,000 miles an hour without our vestibular system sensing that. It's almost like the artificial horizon is parallel with what we're supposed to be sensing. Our body wants to be flat and level, and that's where our body wants to be. That's where the airplane wants to be. Like there's no way that the world could be spinning 1,000 miles an hour, but yet as a pilot, we're always taught that it's not moving, or do a flight plan like it's not moving.
Can I clarify what you're saying? You're saying? Are you saying that we should be detecting the motion of the Earth with our vestibular system?
Yes.
Okay. Did you not just agree with me that the sensitivity is 2 to 3 degrees per second acceleration?
Okay. Yes,
Did you agree
but
with me? Okay, so no, but let me finish.
well,
So you agreed with me that the vestibular system can be fooled, that it is not sensitive enough to detect motions less than 2 to 3 degrees per second acceleration. My question now is, what is the rotational acceleration of the Earth?
supposedly it's 1,000 miles an hour, right?
No. That's the linear velocity at the equator. What is the rotational acceleration in degrees per second of the Earth?
I don't know. I can't feel it.
Okay.
I can't feel it.
Okay. Do you agree? Do you agree that if it was less than 2 to 3 degrees per second, you probably wouldn't feel it?
And I don't feel it. This is what I was trying to tell Mike. I don't feel it.
And I'm asking you a question. Do you agree that if the rotational acceleration of the Earth is less than 2 to 3 degrees per second, you will not feel it?
But I should feel it, or should not.
I'm asking you a question and you keep avoiding. I'm not going to let you do that. I'm going to keep asking the same question until you answer directly. You just have to tell the truth. I'm not trying to trick you. The Earth, you have just agreed with me that the vestibular system is not sensitive enough to detect rotational accelerations less than 2 to 3 degrees per second. This is the reason pilots get disoriented in instrument flying if they're not trained for it. Agree?
Agree.
Now, if the Earth's rotational acceleration is less than 2 to 3 degrees per second, then we should not be able to feel it. Do you agree?
I mean, we don't feel it, right? I mean,
that's not what I'm asking you. I'm saying, do you agree that if the Earth's rotational acceleration is less than 2 to 3 degrees per second acceleration, we won't feel it because the vestibular system is not sensitive enough? Do you agree? Just say yes or no.
I don't have the answer. I don't know.
But you agreed that the vestibular system is not accurate enough to detect 2 to 3 degrees per second acceleration.
Okay.
You agreed to that already. Do you deny agreeing to that?
Again, sir, teach me, please, because I want to learn. Okay. I mean,
that's fine. I appreciate that. Okay. Going back to the basics of spatial disorientation in instrument flying. You're an instrument rated pilot. You know that pilots can become disoriented when flying in cloud if they don't trust their instruments. Agree?
Yes.
Okay. The vestibular system has a sensitivity of about 2 to 3 degrees per second rotational acceleration. You don't have to trust me. You can look that up. It is taught in aviation medicine courses. Every IFR pilot that I am aware of will have learned that. I'm sure you've heard it. Maybe you forgot. That's fine. But the sensitivity of the vestibular system is 2 to 3 degrees per second. Do you accept that?
Yes.
Okay. So any rotational acceleration less than that cannot be detected.
Okay, but why do I feel motion every other time? Like in a car, when I'm doing steep turns, when I'm landing. Today, my student pulled the power out on final, and we slammed so hard, bro. I felt that shit. Like I felt it, bro.
And
like,
so do I. And so do I. You will absolutely feel acceleration greater than that.
We know
you will
when
absolutely,
we feel. So we know when something moves. Again,
we're talking about the threshold. We're talking about the threshold of what you can detect. Okay, let me try and approach this from a different direction. Are you familiar with the Barani chair?
The
Barani chair.
Absolutely not. Wow. Nuh-uh.
Okay. The Barani chair is used for military pilot training to help them understand spatial disorientation.
Oh, okay. Wait. I think that they were like doing this in like the 1940s, right?
They're still doing it, Quincy. They're still doing it, Quincy. Yeah.
Okay.
Okay, they're still doing it. And in fact, Even in civilian training, I've seen it done. I used to do it myself with my students on a basic swivel chair. Okay, so let me put you in the scenario. You're sitting in a Barani chair. It's basically just a rotating chair. If you imagine a typical swivel chair that can spin around, that's close enough. Okay. If I rotated you quickly, you're going to feel it. Do you agree?
Yes.
If I rate, yeah, absolutely.
Because I feel acceleration. Yes.
Okay, terrific. Now, if I rotated you at 1 revolution in 24 hours and your eyes were closed, would you feel that?
In 24 at one. I mean,
one rotation of the chair in 24 hours.
As long as I'm accelerating, I'm going to feel it.
You're not accelerating. You're rotating.
I won't feel it.
Steady rate. You won't feel it.
I won't feel it.
Thank you. That's a good, honest answer. I respect you for that.
Because it says that, you know, you don't, all the airplane is flying level when all the forces are even and unaccelerated. So as long as you aren't climbing or descending or speeding up or slowing down, you won't feel anything. My point is, who felt the Earth accelerating to say, well, that's how we know that it is.
Okay. Is there any evidence, or do we claim that the Earth has accelerated in your lifetime?
Not that I know of. I know that the rule is 1,000 miles an hour. That's what, you know.
Okay. Okay, that's good. That's good. And you know, this is a very productive conversation. I appreciate you staying calm and answering directly. I'll try to do the same too. So you've agreed now that the rotation of the Earth is 1,000 miles an hour. We're talking about the linear velocity at the equator. Agree?
Yes.
Okay. If that 1,000 miles an hour is not changing, there's no acceleration. Do you agree? Yes. You've just told us that you cannot feel when there is no acceleration. If the motion is steady, you're not going to feel it. Do you agree? Right. So by your own logic. Wait. I'm sorry. Just wait. Okay. Go back now. You said to me, at 1,000 miles an hour right now, if it's constant, we don't feel it. I'm saying you agreed that you feel acceleration. You said if the plane is moving at a steady speed, you don't feel it. You don't feel it. Yes, fair. So if something is moving at a steady speed, you won't feel it. You won't feel it. Fair. Okay, thank you. You told me that if you're in the chair and I was rotating it at a steady speed once in 24 hours, you won't feel it. You agreed to that. I would only feel it if I was constantly accelerating the 24 hours. If the speed was constant, I wouldn't feel it even in the chair. I don't feel you can't feel it if it's a constant. Okay, thank you. And I agree with you. So please tell me why you think you would feel a constant rotation on the Earth. There's no acceleration. See, this is the point that we're trying to make is that we wouldn't feel it. So who was the person that felt it and said, okay, I feel the Earth accelerating 1,000 miles an hour. That's how I know that it is. Because on my model, Wolfie, my model works out better. On my model, the sun moves at 1,000 miles an hour, and that's how we get time zones. Because from on the we're going off on a tangent. We're going off on a tangent. We're talking about not talking about the sun's speed or motion. We're talking about being able to feel steady motion. We were talking about the rotation of the Earth and whether we could feel it or not. Barbara, there's a TV remote there, though. Right there. Hello? Yes, sir. Yes. Hello, that's okay. I know you've got life to deal with. Yeah.
Hey,
So, the question.
they're always saying you're always flying planes. You're always flying planes. So
That's okay. No, that's all good. So let's just finish off this. So you
Sure.
agreed that you agreed that you feel acceleration, but you cannot feel steady motion.
yes.
Okay, so our statement is, our claim is that because the Earth is rotating at a steady rate, there's no acceleration to that rate of rotation, you're not going to feel it. That is perfectly normal when we know the sensitivity of our vestibular system. That's our argument.
Okay.
Okay, so are you still making the claim that we should feel the rotation of the Earth?
Well, I'm saying, how can that be science if no one has ever felt the acceleration? Like, who was the person that felt it accelerating to say that it is? Like, how did they know?
It's
like,
well, it doesn't really matter. It doesn't really matter.
Well, what do you mean it doesn't really matter?
Now,
But because
the argument has the Earth's rate of rotation changed appreciably in either of our lifetimes?
Again, how do we know it's rotating if we can't feel it? That's what I'm saying. Because to me, if I look up and see the sun moves, the sun actually moves.
Yeah, we'll get to the sun. We'll get to the sun. We'll get to the sun. Now, I'm simply asking that why do you think we should feel the motion of the Earth right now if there is no acceleration?
But my point is that we shouldn't feel it if it's constant. So who was the person that felt it? How did they test it if they can't test acceleration? If you can only feel acceleration, how did they test the acceleration if there is none? Because they didn't. Someone said
that's a different argument.
This.
That's a different argument. That's a different argument. And I'm simple. So you're now agreeing that if the motion of the Earth is constant, there is no way for us to feel it with our bodies.
There's no way for us to feel it or to even test it.
Okay. I'll disagree with how to test it. We can talk about that separately. It's not specifically aviation related, but I have done experiments on that too. Okay, so we finish off that point with you agreeing that because of the steady motion of the Earth, our vestibular system is not accurate enough to detect it. Do you agree? And we can, if you say yes, we can finish off there.
That's strange that it does detect every other motion except for the one of the Earth.
but it doesn't. But Quincy, it doesn't detect every other motion.
What do you mean?
You just agreed that if you're in a chair rotating at one rotation in 24 hours and there was no acceleration, your body would not be able to detect that. You agreed to that.
I got you. Okay, I got you. Yeah, you're right. So if they say the Earth spins and we don't feel it, we don't feel it because we can't detect the motion. How do we know that they were able to test that? Who knows? It's just something that they said.
Okay, no, that's good. So we're both in agreement that our bodies are not accurate enough to detect steady motion.
Yes.
Thank you. All right, that's good. Now let's talk about the artificial horizon. Okay, have you seen my video showing the internals of the artificial horizon?
No, but I do know how it works now. Now, me and Mike had a question, and so I say to my students, keep the airplane level. Level to me means flat. Mike tends to think that flying level is not flying flat.
Okay. Can we talk about the artificial horizon?
Sure. Okay.
So you haven't seen my video showing inside the artificial horizon. Have you ever seen inside a real artificial horizon yourself?
Absolutely. With the tubes to the vacuum system and the rotor buckets on the inside with the three three. I said yes, sir. All the
Fabulous.
time.
Okay, terrific. So you agree that depending upon the design, of course, that the standard artificial horizon uses a correction mechanism via pendulous vanes. Are you familiar with that term? Yes.
Yes, sir.
And those pendulous vanes are forced on by gravity, or they're acted upon by gravity to sense the direction of down, and they will pivot either way, and they will result in a correction force on the gyro to always restore it to horizontal based on the direction of down that those vanes are sensing. Would you agree with that?
Yes.
Okay, perfect. Now we could close this one off very quickly. Now, the flat Earth argument is that the artificial horizon, the gyro in the artificial horizon, is set when powered up and never changes. Their argument is that if we fly around a curved Earth, that artificial horizon should show the aircraft pitching down continuously.
Okay,
However,
Wolfie, this is an easy one. Now, you know, Wolfie, that thing is flat and straight. If we kept flying at the same altitude, you know what? I'll even tell you one more. I often had a challenge, right, to throw online called the Flat Earth Pilot Challenge. And all we have to do is any pilot and any airplane take a picture over 200 miles and show the curve, because the artificial horizon is just that, an artificial horizon. And if something's horizontal, then it's flat.
Okay, we're getting away from the point. But the argument flat earthers make is that if the gyro in the artificial horizon was truly rigid in space and the aircraft was following curvature, that should appear as an indication in the artificial horizon. Have you heard that argument from flat earthers?
I heard that to somebody who wasn't even a pilot. And when they told me that, I said, whoa, I've never thought about that. And we relearned it again. And now I agree with that argument.
So you agree that the gyroscope in the artificial horizon is always rigid and the pendulous vanes do absolutely nothing. Is that what you're saying?
Well, it only works on a flat plane.
No. What do the pendulous vanes do?
There's no way that the gyro could work on a ball.
Quincy, what do the pendulous vanes do?
Huh?
Quincy, you told me that you have seen inside an artificial horizon. You have told me that you told me that you have seen the pendulous vanes. What do the pendulous vanes do? What is their purpose?
The pendulous vanes, they're there to, does the air pressure escape one way to get it right? The air spins the rotor buckets, and then, because like now I've been flying the G1000 now, so you know I'm all glass now, so it's been a
that's okay.
Wild.
The G1000 is an impressive bit of gear. It's amazing. I agree. It's fabulous.
Man,
the question is, what do the pendulous vanes do?
I forget.
Okay, the pendulous vanes are based on gravity. They sense the direction of gravity or acceleration if you're in a turn. They then act by producing an asymmetrical force on the gyro that causes it to precess to align with the sensed direction of down. That is
so down. So down could mean like weight, could mean level, could mean to the center.
Down is very simply, if you have an object and you drop it, the direction that object moves. That is what I call down.
Okay. So then how does that work on a sphere? Because if you kept flying, down would eventually be sideways. Now, if the
Correct.
Earth were
Down on a sphere
would
is always
be sideways, but down on a flat Earth is always down.
okay. Down on a sphere is towards the center of the sphere. Okay. So if you go 1/4 of the way around a sphere, your direction of down has changed by 90 degrees. Can you visualize that?
And that's sideways.
Okay. It's sideways with reference to the starting point, but it's not sideways with reference to the finishing point.
But on a flat Earth, my model, down is just down, and that's what makes sense.
Sure. Well, no, down towards the center of the sphere also makes sense, because down is not sideways if you're at that position. If you start at the North Pole, and North Pole, you call that up, and you move 1/4 of the way around the Earth, you're now on the equator. Would you agree?
Yes, and now down is now sideways at 90 degrees.
It's sideways referencing the North Pole, but it's not sideways referencing the equator. Down is now down towards the center of the Earth.
Okay, but on a flat Earth model, down is always down.
So yeah, down is always down too on the globe, but the direction changes. It is. Down is always towards the center of the Earth. Down is always down on a globe.
But if you're on a globe and like you're on like Antarctica, you know, which way is again down would be up again. See, it doesn't work.
Are you saying that north is up and south is down?
I'm saying that every compass always points to the North Pole because there is only the North Pole.
You're deflecting. Sorry, Quincy, you're deflecting. We're not talking about compasses. I'm saying, are you saying that north is up and south is down?
North is not up. North is the center. North is straight, just like the VOR.
So when you say down is sideways at the equator, sideways with respect to what?
No, down. I'm sorry. The North Pole is the center. To fly south would be to fly outwards. So down is just down.
Okay. You're looking at a ball. You're looking at a ball.
But I'm not looking at a ball. No, I'm not. I'm looking at a disc. You're looking at a disc. Which way is down? Okay, it's down.
Okay. Let's get back to the question. Pendulous vanes. Pendulous vanes. Do you agree that they can correct the position of the gyro in the artificial horizon?
Yes.
Okay. So therefore, it is never consistently rigid in space, is it? If it's being corrected, it's not maintaining a single attitude in space.
But it's trying to do that, though. It's trying to show you that I'm at 5,000 feet. So when I bank the airplane to the right, it shows the bank, and then when I turn back, okay, it's showing me that. It's showing me where I'm back to being.
Yeah, you just said the artificial horizon is showing you that you're at 5,000 feet. It doesn't do that though, does it?
I'm sorry. Well, when me and Mike were talking, the example that we used was 5,000 feet. But no, you're right. It doesn't do that. It shows you where the horizon is.
Okay, so why does the gyro in the artificial horizon need a correction mechanism, in your opinion?
Why does it need a correction? Why does it need a correction? I know in the older the older planes, like because I fly some older ones. When I first start up without vacuum pressure, it doesn't read right. It doesn't show me level. So with the right amount of vacuum pressure, it spins up the gyro to show me level. And you're asking me, say again?
Okay. If the pendulous vanes in the gyro are able to correct its position, why does it need this correction?
Why is it needed correction? Or are you asking me how is it being corrected, or why is it being corrected?
No. It's being corrected. It's being corrected by the pendulous phanes, and I explain that very clearly on my video, actually demonstrating it occurring, and I show how the pendulous phanes are moving at various attitudes to always restore the position of that artificial horizon with respect to the sense direction of down. That's fine. I'm asking why, if the flat earthers claim that a gyroscope is always rigid in space. If it's always rigid in space, why does it need correction mechanisms?
I don't know.
Okay. You're familiar with acceleration and turning errors?
Oh yeah. Anders. Yeah.
Yeah. Okay. So we have errors. We have acceleration and turning errors that can cause the artificial horizon to become inaccurate.
Mm-hmm.
We have bearing friction that could cause precession. We have acceleration in tight turns or aerobatics. I don't know if you've flown aerobatics. I've done a lot of it. You can really throw that artificial horizon into a spin, literally. By doing aerobatics.
Right. And then it'll tumble over.
Absolutely, and then it takes a long time to correct itself.
Right. In fact, at the school that I'm in, they don't even want us doing spins because it can really damage them.
Absolutely, and I agree with you. You know, if you need a proper artificial horizon to cope with aerobatics, or you need to cage it. You need to cage it during aerobatics, in which case you're locking the gimbal. Yeah, okay, that's fine. So you would be happy to agree that claiming the gyro in an artificial horizon is always rigid in one position is actually not true. You agree with that?
Okay.
Okay, thanks. Terrific. Now, the specification for the correction rate on the artificial horizon that I use in my demonstration is 2 to 4 degrees per minute. So if there is an error for whatever reason, whether it's due to Earth curvature or aerobatics or acceleration or turning errors, if there is an error, the correction mechanism, the pendulous phanes, will correct that at the rate of 2 to 4 degrees per minute. I show that in time-lapse videos in my own video footage. So 2 to 4 degrees per minute correction. Would you have any reason to disagree with that?
No.
Okay. If we are flying at 450 knots, that's
at your speed.
Yeah, I understand, but the faster we go, the worse it is for the globe if the flat Earth theory is true. So 450 knots. I use that number because it gives me 1 degree of Earth, of flying around 1 degree of Earth every 8 minutes. Okay, 450 knots does that cleanly. In 8 minutes, we fly 60 nautical miles. Okay, so basically what we have is 1 degree of curve in 8 minutes. Now,
okay,
to remain level to the pilot's eyes, if you're flying around curve and you're going over 1 degree of curve every 8 minutes, for that artificial horizon to appear level at all times, it would only need to correct 1 degree every 8 minutes. You agree with me?
Yes.
Okay. The specification for the gyro is 2 to 4 degrees every minute. So it is easily capable of correcting 1 degree in 8 minutes. Would you agree?
Okay.
Okay. So now you would agree that if we are flying over a curved Earth and the artificial horizon to the pilot's eyes is always remaining level, that could be entirely due to the correction mechanisms doing their job.
Well, if you kept flying though, because you got to look and see, not only are we talking about the attitude indicator, but we're also talking about the altimeter on the globe.
We're talking about the attitude indicator.
Well, on the globe model though, two things tend to be happening that we don't observe happening. For one, the attitude indicator is always straight, and two, the altimeter doesn't seem to move. If we live on a globe, if we live on a globe, the altimeter should be off as we fly, because we would be flying off into a space, right? Supposedly.
Okay, we'll come to that. We'll just stick in the back of your mind the terms surface ceiling and absolute ceiling, because we'll come to back to that. Okay, but we're talking about the artificial horizon now, and you stated that it's always level, always showing level as we're flying. We're moving across 1 degree of curve every 8 minutes at 450 knots. Okay.
But what's the height of the curve? It's 8 inches per square mile.
No.
So
it's 1 degree every 60 nautical miles. It's 1 degree. The curve is 1 degree every 60 nautical miles.
So that's what in feet.
It's 1 degree. You don't measure curve in feet. You measure
Well, I'm saying if the Earth is a sphere, are you flying around the sphere, or are you not?
We're trying to establish a single point on the artificial horizon. We're not talking about how many feet of drop based on 8 inches per mile squared. We're not talking about that. We're talking about 1 degree of curve every 60 nautical miles. That is 1 degree of curve every 8 minutes flying at 450 knots. You agreed that the correction mechanisms can correct errors at the rate of 2 to 4 degrees per minute. You agreed to that earlier. So if the artificial horizon has to correct 1 degree of curve or 1 degree of error every 8 minutes, it is certainly capable of doing that. Would you agree?
On a longer distance,
one degree, 60 nautical miles.
No, because wait a minute. In class A airspace, you're at a flight level, right? You're at a flight level. How are you maintaining the flight level if you're at that one degree for so many miles? At some point, you be off your assigned level, right? Exactly.
You're trying to introduce a different argument. We're not talking about the classes of airspace. It doesn't matter. It doesn't matter.
It does matter because you're level. They call them flight level. Hey, sir, please climb to what? Flight level 290. Flight level.
Does the artificial horizon know what class of airspace you're flying in?
No, it doesn't. But it tells you but it tells you that you're level. That's what it does do.
I'm not disputing that. I'm not disputing that. I'm talking purely about its capability to correct errors. You agreed that it can correct errors at the rate of 2 to 4 degrees per minute. That is stated in the instrument manual. It can, if there's an error, if it detects an error, it can correct this error at 2 to 4 degrees every minute. Okay, you agreed to that. If you want to retract your agreement and go and look it up yourself, I'm quite happy to wait, but you have already agreed to that. Now, that rate of correction is much faster than correcting 1 degree in 8 minutes. Would you agree?
What is the correction rate in feet?
Does the artificial horizon show you indications in feet?
But they go together, Wolfie.
Does the artificial horizon show you indications in feet?
No, it doesn't. But the altimeter does, and they both aren't doing what that they would do on a globe. Is the point. But the point
we will talk about the altimeter if you like, but let's finish off with the artificial horizon. Happy to talk about the altimeter next. The artificial horizon is what we're talking about now. We're talking about the ability of the artificial horizon to correct an error of 1 degree every 8 minutes. Do you think the pendulous vanes, the correction mechanisms can do that?
Not according to the curve of the Earth, no.
Okay, but you already agreed that it can correct
They
an
make
error.
corrections, but the corrections that they're making are not due to the due to the curve.
We're not arguing.
Veins
We're not arguing. We're not arguing exactly what it is correcting for. We're arguing if it is capable of making that correction.
not for the curve. No,
No. Can it make a correction of 1 degree every 8 minutes?
1 degree of what?
1 degree of error.
Error. Yes.
So it can. So if there is 1 degree of error in 8 minutes or over 8 minutes, it can correct for that quite easily.
Yes.
Okay,
And
so
the degree in error is not degree in curvature.
okay, it's irrelevant. It's irrelevant. You have agreed that the artificial horizon can correct 1 degree of error in 8 minutes. Are we happy with that?
Sure.
Okay, I'm happy with that. Is the audience happy with that? I can see you, MC Toon. If you give me a thumbs up, I'll accept that.
I'm happy with that.
All right, thanks.
Okay.
All right. Now the altimeter. You talked about on a globe Earth, you believe the aircraft would just continue climbing. Is that right, Quincy?
Either climbing or descending, but it wouldn't be, again, me and Mike use 5,000 feet. And my point is, at 5,000 feet, if I flew for, I don't know, I'm on California. If I flew from here to from here, I drew a line, whatever. I'm going to be level the whole entire time. Like, there's no way that I'm flying level at the same height.
Okay. So I'm just trying to. I'm just trying.
It's spinning too, right?
I'm just trying to understand. I'm just trying to understand your argument with reference to the altimeter now. Are you claiming that on a globe Earth, if you're flying level, you would be climbing? What's your argument in relation to the altimeter?
8 inches per square mile. So even after even after about 200 miles, you'd probably drop about 400 or 500 feet. I'm not good at the math. I'm not good at doing the math.
That's okay. And you're a flying instructor? You're a flying instructor? You're a flying instructor?
Yes, I am.
Okay, you're teaching your students how to fly straight and level. This is the straight and level lesson, okay? You teach this, you're teaching the student, and you have given him an altitude of 4,000 feet to fly, okay?
Right.
He's looking at the altimeter, he's looking at the vertical speed indicator, and you have asked him to maintain 4,000 feet. If he notices the aircraft has climbed slightly, what does he do to correct?
He probably noticed the VSI move up a little bit first, then the altimeter would move. He has to lower the nose, pitch back down to where he was.
So you agree that when a pilot is flying, they don't just let the airplane climb, they actually lower the nose if it climbs.
Yeah, but if he descends, then he has to climb too. So
I agree. I totally agree. I totally agree. You're always making corrections to maintain.
You're always trying to what I teach my students: keep the flatness. Keep the flatness.
Okay. So can we agree? Can we agree that to fly an accurate altitude, we are always making corrections?
Yes.
Thank you. That's been my whole argument for years. Correct. Thank you. Okay.
Small corrections. Corrections. I was just to tell somebody today. Don't use big corrections. Small corrections.
Absolutely. Yep, I totally agree. And I used to teach my students just to do it with fingertip pressure. You don't need any more than that.
Exactly.
If the plane's all right, perfect. Now, another argument some flat earthers have claimed is that if you make no corrections, the plane will fly off into space. Have you heard that?
That's what I believe.
That's what you believe. Okay.
Yes.
What aircraft do you fly? What aircraft do you fly?
Cessna 172.
Okay.
Archie?
What is the published service ceiling for that aircraft?
About 16,000.
Okay. What does that mean?
So that means that at any further height, an increase in angle of attack will cause a stall. No, wait, is that absolute or service? Service is
yeah. So yeah, I hear what you're saying. You're talking about absolute ceiling. I'm talking either or. It doesn't matter. You can explain.
okay,
absolute ceiling.
but
Yeah.
at any further higher angle of attack, the plane's gonna stall.
Okay. So you agree that even if you tried, you could not get your Cessna up to 25,000 feet, even if you tried to do that.
No way.
Okay, thank you. So how could it possibly fly off into space?
Well, I mean, obviously it can, but on the globe model, this is what I was telling Mike. If we're flying lines, you can only draw a line over this is where we're coming into flight planning, because drawing a line over a flat plane makes sense. Drawing a line over a sphere makes an arc.
We're talking about flying off into space. Okay.
Right. Because
you talked about the absolute ceiling of the aircraft. Okay. My aircraft can get up to 51,000 feet, but there is no way I could take it up to 70,000 feet. It just
there's no way.
It doesn't have the performance. So if I do nothing, if I'm flying on a globe Earth and I do nothing, and the airplane is flying a straight line, which means it would climb, there would be an aerodynamic limit at which point it could no longer climb any further, and the nose would automatically drop, whether it just be due to aerodynamic stability or by stalling. So it could not fly off into space, could it?
No, because the Earth is flat and it flies straight and level, and you always fly at your assigned.
Okay, so the aircraft cannot go above a certain altitude based on aerodynamic and performance limitations.
Yeah, right. Exactly.
You agree with
because
that? You agree.
It doesn't.
And altitude, we can simplify it by saying the distance above the ground. You know, it doesn't have to be technical. We don't have to talk about QNH or pressure levels or anything. Just a layman's explanation of altitude is how high you are above the ground. Would you be happy with that? Okay. So we know that the aeroplane cannot go above a certain altitude, which is a certain distance above the ground, due to aerodynamic and performance limitations. Do we agree?
Right.
Okay. So based on that, even on a globe, it cannot go above a certain distance above the ground, flying in a straight line. It will hit an aerodynamic limit, at which point it will no longer expand its distance above the ground, and it will just naturally follow the curve due to aerodynamic and performance limitations.
Okay, but when we fly, we don't have to take it back into the curve. Nowhere in the curve do we do our flight planning. Nowhere.
All right, we can talk about flight planning soon, but let's finish off this one. So you agree the claim that a plane could fly off into space is ridiculous because of aerodynamic and performance limitations?
I believe a plane that if we're on a sphere, all right, ain't nobody flying no straight line, Wolfie, over like the fact that we fly level proves that we're not on a sphere. We're not on a sphere. There's no way we're in a sphere.
Okay.
No way.
You're just making claims now without any reference.
I mean,
we're talking specifically about the performance of the aircraft.
Because
you
know what I mean.
You agree there is an absolute ceiling. The aircraft cannot go above that.
Yes. Okay. Right.
So if you try to go above that, then simple physics will stop you.
Right.
Yeah. Okay. So flat earthers say that and I'm not saying all of them, I'm not generalizing, I'm saying some flat earthers claim that if the plane flies straight, it would fly off into space. But you and I now agree that there is a physical limit where it could not fly any higher due to aerodynamic and performance limitations. So there's a natural barrier preventing it going off into space.
Okay, but
Okay, happy with that?
are we flying around the curve?
No,
Like,
we're just talking about how high that aircraft could go. On a flat Earth or a globe, it doesn't matter. We're saying that there is a limit that will naturally prevent it from flying off into space if it's flying on a globe. And that limit is the absolute ceiling, which is dictated by aerodynamics and the performance of the aircraft.
Okay,
Are we happy with that, Toon? Happy to just move on from that one?
sure.
Yeah, I'm happy.
Okay, all right. So what was the next point you'd like to discuss? Flight planning.
The fact that we're drawing lines over flat, like the charts that we use to fly with are flat.
Okay.
They're a flat.
Can I ask? And I'm not being condescending. I'm just trying to understand your experience so that I can pitch my questions accordingly. Do you have any international experience?
No.
Okay, thank you. Do you have any experience with electronic flight planning?
Like
Universal, Jeppesen, ARINC, anything like that?
Sometimes I use ForeFlight.
ForeFlight, okay. When you use ForeFlight, when you zoom out on the map, what does it show you?
It shows a globe.
Okay, thank you.
But
now,
it's
do you think
not. But it's not a real globe. It's just a computer one though. Like there's no actual.
Of course, it's not a real globe. Of course, it's not a real globe. But it's a mathematical representation of a globe.
Only when you zoom out. When you zoom in, it's flat.
Well, it's not flat, and you can prove that quite easily when you just move the track north or south.
But when you zoom in, it's flat. But
it's not flat. It's not flat.
You never could correct for anything though. No.
We're okay. We're talking about flight planning. We're talking about flight. Okay, you use ForeFlight occasionally. Okay, you agree that when you zoom out so that you can see the entire map,
or even this, man. Here's one better for you. Day one of flight planning, even VFR, I use a regular chart. I say, student, draw your line. The chart that we use is flat. We use flat charts.
Okay, what charts do you use?
Over here, I use the San Francisco sectional. Yes, chart. Yeah.
Sectional. Okay. Are you familiar with the World Aeronautical Chart series?
Yeah. So when you're flying from larger, when you're going on larger routes, yeah.
Sure. The World Aeronautical Chart. It's what I learned to navigate on in Australia. Okay. We had the World Aeronautical Chart. Do you know what the scale is of the World Aeronautical Chart?
Oh, I don't. Is it 1 in 500? I know it's the biggest one.
Yeah, it is. You're right, and it's 1 to 1 million. Correct. So the World Aeronautical Chart on every World Aeronautical Chart, it will tell you the type of projection. And as Toon said earlier, the projection is the Lambert-Scott formula. You'd not heard of that?
No.
Okay. Let's just do a quick Google search on USA sectional.
I'll get the link. I have it too. I'll put it in the chat for people to look at.
Thanks. Sorry, I should have had this prepared earlier. I just want to get a good reference. Yeah.
There, and I'll give you. Yeah, there's a link to the actual VFR raster charts, which is what I just put in there. I can send that to you, Wolfie, unless you already got it.
No, I don't have it.
I'll put it in the chat for both of you to see if
okay.
There you go. And then I think is it San Francisco that you use?
Yeah.
Okay, so people, you can scroll down. You can look at the San Francisco one, June 17, 2021. And then there's a GeoTIFF or a PDF. Look at the PDF. It is a gigantic PDF. It'll take a little bit of time to render and a good amount of time to download.
Sure. I'll have a look. Okay. While we're doing that,
Wolfie,
Mhm.
Mike's son is learning how to fly too.
Yep.
Fabulous. That's good. I wish him every success. I'm just trying to find your link. My chat's way behind.
And I put it in the Zoom chat.
Okay. Let's have a look.
What are you flying? CRJ?
No, it's a I've actually just typed on the Global 7500, which is their latest model.
Wow.
Yeah, I was just so happy to do that. It's
Oh, that's cool.
it was delayed for over 12 months, my type rating due to COVID. But last February I was over in Dallas for 5 weeks, and yeah, it's a pretty impressive piece of kit.
Were you with flight safety?
I actually did it with CAE at Dallas
Oh, wow.
Airport. Yeah. So yeah, they used to be owned by Bombardier, but CAE has taken over. Okay, I can see that link. And what are we doing? Okay, let me just bring one of them up. We're basically trying to look at how this chart is actually made, what the projection is. And, you know, it's a Lambert's conformal, and a Lambert's conformal chart will have something called a standard parallel. Are you familiar with that, Quincy?
No.
Okay. Standard parallels are the two lines along the chart where the scale is perfect.
Okay.
Okay. It is taking a while for me. Yeah.
Are you familiar with the E6B?
Absolutely. I haven't used one for a
Flight
while,
computer.
but yeah, absolutely. Haven't used one for a
Okay.
while, but yeah, absolutely.
So I teach some of my students how to do it, but before they start doing the flight stuff, and we correct for easterly or westerly variation, right?
Yeah, absolutely. Yeah.
What are we? I always tell this to instructors and pilots, and they never have the right answer. What are we correcting for easterly or westerly variation?
What are we correcting for? We're correcting for the fact that the geographic north is not located with the magnetic north pole.
So can you make that easy for the students to understand? Like, what is that?
Well, there's a number of mnemonics you can use. Variation east, magnetic least.
Okay.
Variation
west is best. Yeah, but what does that mean?
Variation east, magnetic least. It means that if your variation is 10 degrees east, your magnetic direction will be a lower number than the true direction.
Again, that's so complicated. I tell students like this.
Yeah.
Because the earth is flat, east to west are not straight lines. East to west go in a circle. East to west go in a circle. So you are correcting for?
Can I ask just a clarify? When speaking to your students, do you actually say, since the earth is flat, this?
I don't really, you know what? Some of my students know me for a while. They don't agree. Some of them people agree. Some folks don't. But like I say, people don't even use the E6B anymore. Again, it's all of the flight planning stuff. Mike, is all new school now. There is no more charts and plotters. But the way that I learned was a chart and a plotter and an E6B and drawing lines, and all this stuff that I'm doing works on a flat world. But east to west are not straight lines. So what we use the E6B for is to, if we never corrected for east or west, and we flew in any direction, we'd always go towards south. If we never corrected for east or west, we would always fly south, because east and west are not straight lines.
Okay. Okay, Quincy, I'm just talking about the chart projection again, and I've just Googled the phrase standard parallels, because I can remember as clear as a bell when I was just doing my initial training, my initial commercial pilot training. The first thing they showed us was the globe. They showed us how the maps are actually, that's what they showed us, I'm just telling you. And they showed us how the various different maps are produced. They showed us how the Lambert's conformal projection works. And as a result of that projection, there are two lines on the chart, and on every WAC chart, it will actually tell you where the standard parallels are, which latitude the standard parallels are. If you do a Google search for standard parallel, it says this: standard parallels are lines at which there is no distortion in the map projection. Standard parallels are used in both conical and cylindrical projections. They theoretically touch the Earth's surface. So if you can find a WAC chart, and you will see that it states clearly it is a Lambert's conformal projection, and it will tell you what the standard parallels are. So that is solid evidence that the chart is actually produced from a globe.
Mike?
Yeah.
You guys win. It's a globe.
No, I'm not trying to be smart. I'm just trying to.
No, I mean because you know, it's again, at the very end of the day, right? One of us are right. Okay, one of us are right. One of us is a pilot who is really trying to learn, you know, really trying to learn, you know, and one of us thinks that he already knows. And
no, Mike, that's not what's happening here. I have not tried to belittle your experience. I was an instructor at one point. I only had a private pilot's license at one point. I was teaching students in Cessnas at one point. I have absolute respect for what you're doing. I don't feel that I'm superior to you or anything in that respect. I fully respect what you do. Okay, I'm not trying to belittle what you're doing, and I respect that maybe you have not encountered some of these things I'm talking about. By telling you about standard parallels, Lambert's conformal charts, you are learning. Are you not?
I am learning.
Thank you. And you know, and if I can share some knowledge with you and you learn from it, then we're both happy. So
there we go.
So yeah, so like I said, I think this has been a very productive conversation. You've been polite. We've respected each other's opportunity to talk. If you're happy to finish, I'm happy to finish there. I'm quite happy with the conversation.
Well, okay. Just on a side note, could we can finish here, but could you explain to me when you're in a jet and you have an upset, like what are the aerodynamics like as opposed to like how are people losing control when they get to, like, you know, higher altitudes, or I think they call it Coffin's Corner.
Yeah, Coffin Corner. I knew what you were getting at. Coffin Corner is it's the space, if you like, between the critical Mach number where the airflow over the wing becomes supersonic. That's at the high speed range, and the speed at which the airframe will stall aerodynamically. Now, because the air pressure reduces as we go higher, I think you will agree with that. Air pressure reduces as we go higher. Up at 51,000 feet, it is a small fraction of what it is at sea level. And as a result of that, to fly, we need to generate dynamic pressure on the aircraft. That's how the airplane flies, by dynamic pressure over the wings, creating lift. If we have less air or less dense air, we have to fly physically faster to generate the same dynamic pressure or indicated airspeed. We're talking about difference between indicated airspeed and true airspeed. And you agree that they change as you go higher?
Right.
Indicated versus true airspeed. You would teach that as an instructor. Every instructor would teach that. So at high altitudes, 51,000 feet, we have a very small range between the aircraft actually stalling or exceeding the critical Mach number. Now, the old Global I used to fly, if I was up at 49,000 feet, that gap would only be maybe 10, 15 knots. You know, it's not much. So I've got an upper limit and a lower limit, and there's only 15 knots to play with. In smooth air, not a problem. Smooth air is not a problem. If you're in very turbulent air, then yeah, you're going to get speed variations. And those speed variations could go from, you know, taking you over your critical Mach number to below your stall speed. So you're going to have problems there. In severe turbulence, we would just go down. We would just go down to a safer altitude. And, you know, the Global Express XRS, my old model, down at 43, 44,000, it was fine. You had a nice margin.
So is all that like, so I'm assuming all that's like an autopilot, right? Like there's no hand flying at the higher altitudes.
We generally do just fly on autopilot. Yeah, absolutely. We fly on autopilot. I have many times just taken off autopilot and just had a hand fly, you know, because, you know, you can sit there for 15 hours and not even touch the controls. But, you know, I like to keep my hand in all the time. So quite often I'll hand fly all the way up, you know, take off. And our SOPs say that we can turn the autopilot on, you know, less than 1,000 feet after takeoff, and you can do that, and you can sit back and drink your coffee and let the plane do everything.
So is the airplane less controllable as you get higher by hand flying? Is
Yeah, absolutely, it's more sluggish. It's and the best way to describe it is if you fly your Cessna at 120 knots, you have stiff controls. You fly it at 85, 90 knots, it's going to feel more sluggish. You agree with that?
Okay.
Yeah, it's the same sort of thing. It's because at 50,000 feet, you know, my Global has indicated airspeeds under 250 knots. You know, at lower altitudes, its indicated airspeed can be, you know, well above that, well above 280. So of course, you've just got that aerodynamic stiffness on the controls and the associated responsiveness. But yeah, absolutely, hand flying at high altitude, it feels sluggish. You know, it feels like you're driving a truck through mud, but that's just part of the fun. That's why I try to just always keep my hand in, you know, in the event of any emergency. If we lose the autopilot, at least I know that I've experienced that and I've done it, and I try to do that regularly. Most pilots, well, we're Part 91, so we're not as restricted as 135 operators or airlines. You know, we have a lot more.
Man, you're flying the jet under Part 91.
Yeah, absolutely.
Lucky guy you are.
Yeah, I know. That's why I keep flying. You know, I love my job. It's just basically they pay me to just fly the toys that I love, you know, and our operation is so unrestricted and we have so much control over how we do things. It's almost like it's my operation. But yeah, you know, we could put the autopilot on at 1,000 feet, let it do its thing, but quite often I'll just hand fly. I'll hand fly all the way up to 43,000 just because I can, and it's good experience just to do that. So once you're up there, you know, you know, do it for a few minutes and then okay, time for a coffee, call the flight attendant, autopilot, and have your lunch.
Hey,
cool beans.
I have the San Francisco chart on screen, and I can share it to you too if you want to look at it quick.
Okay. Yes, please.
All right, so there it is, zoomed in to the Lambert conformal conic projection, where it says the standard parallels are 33 degrees 20 minutes and 38 degrees 40 minutes. And I'll zoom. Do you see that there, both of you?
Yeah,
absolutely, I do.
All right. So I'll just back out a little bit. So if you're using this sectional chart, this is the San Francisco sectional chart. That's the same one that you should be using there, Quincy. So does that look familiar? Is that where you're doing your routes?
Yeah. Okay. Yeah. I did my ATP out of Riverside just for info. My US ATP, I should say.
Okay.
Yeah.
Yeah. Well, there it is. So, all right.
Okay.
Just wanted to, because I got it going. So.
Yeah, that's great. All right. Well, look, I'm happy, Quincy. I think it's been a productive chat. If I'm happy to keep going, or if you've had enough, I don't mind either way. Yeah.
Yeah, Mike.
It's
Mike.
Yeah.
It's been good, man. I needed just to talk. So, I'm still, I guess I'm still set on my ideas, and you guys are still set on yours. And it's cool to come to a point of, agreement to disagree. But I just wanted to be known that I'm not just some flat earth guy on YouTube. I actually do the work and the homework. So.
Yeah, I've no reason to doubt you're a real pilot, and you're probably quite a good, competent one. So good luck to you.
My Mike?
Yes.
We're all good, sir?
Oh, yeah. It's been good. Thank you for coming on. I got a little heated earlier, but, you're a great guy. So thanks for coming.
Okay.
Thanks, Mike. Enjoyed that.
All right, Wolfie, man. You guys take care.
You too. Okay, have a good one.
Sorry, Barbara.
Yeah,
I'll
I'll send you out so that you don't. There we go. Okay.
Yeah, thanks, Mike.
Yeah, thank you for coming on. I've got a few super chats to read, and then I'll wrap it up. It's been a good long stream. It kind of went a bit long.
All right.
But all right. Well, thanks a lot, Wolfie, and we'll catch you later, I guess.
Thanks.
Feel free to stick around if you want for the exciting super chat readings.
No worries.
All right. Generally Shady said, if you can't math or science, never be a pilot. I thought he'd maybe have a little more math or science, but I don't think he did. Robert Williams says, in a holding pattern for BWI directed to land at 33L, what compass heading are you on in the glide path? Oh my goodness. How could I know that? I don't have any reason to think that he's not certified. We looked him up. All that is public. If you know their name, you can look it up. So that's how Wolfie knew that Bob Nodell was never a multi-engine certified pilot. So land at 33L. 33, is that that's the bearing, isn't it? The magnetic bearing. I don't know what that means. So Indy Tiger says, all maps and charts show that the Earth is a globe if you don't know what to look for, because they're all projections of a globe onto a piece of paper. Oh yeah, exactly. And that's sad that he did not know that the charts that he uses and learned on are are actually projections. Connell Silverfur says, this Flurf pilot flies from one subject to another. Why do they all have such short attention spans? Well, yeah, he did seem to have a pattern. He would get to a spot that he couldn't answer, and then he'd move along right away. He would introduce a new topic quick as he could. Schrodinger's cat says, why is a single engine pilot wearing an airline pilot's uniform? That I was going to ask him, but it had been a while. We'd been in there for a bit long. So he does train at like a school. So maybe that's part of the school. I don't know. Or some people were thinking it might have just been more of a costume. I tend to think it's from the school. So Alyssum says, I am comforted by the fact that you will never fly large passenger aircraft. Yes, I don't think he would get past. There's certain levels you cannot get past. Yep. Kaivera Art says, I'm terrified that this man is a pilot. Lord in heaven, let him never be flying my plane. Well, since he does just single engine planes, you'll know. It's in a single engine plane. You're pretty close to the pilot usually. Cottle Silver Fur says, Flurf can't tech with his own internet. We expect him to be able to use a more sophisticated airplane tech. Big X to doubt. Alyssum Toon Wolfie's email has an extra 2 in it. Yeah, I think that the link must have gotten blocked. Sending it to him. So, and then Chris Hoffman says, Empty Toon, yeah, gave me Wolfie's email. You forgot the extra 2. Also, if you can't show a fart on camera, then farting doesn't exist. Oh, the 13-year-old in me just loves that comment. Drop a haha in chat if you think he's nuts, says General E. Shady. Did we get any ha-has? Let's see. Connell Silverfur says he doesn't know how cars work. How do we think he's going to know how rockets work? Oh, I know. He got the law of motion right, and then got wrong on pushing off of air. And I mean, he doesn't understand things, and that is so common for flat earthers, that they don't understand things, and that is their only debunk. So, like Level Earth Observer, he doesn't understand things. He's in the chat. How you doing, Level Earth Observer? Or Leo. Alyssum says, I've searched for a FE pilot for years, and this is what we get? This guy's pathetic, even for a flatty. I am disappointed. Well, Alyssum, what else would you expect? You don't get to thinking that the Earth is flat through logic and reason. So, Kevin Brown, he's got Wolfie on here. I've heard that voice for years, but never live. MC Toon Rocks. You know, that is the first time I've spoken with Wolfie, and it was not me talking to him. So Wolfie is, I've emailed with him before, and I have his email address in my book, in my address book. Let's see. Hold on a second. I need to stop. I need to close down the stream. Come on. There it is. All right. Closing that. I'm closing the Zoom call. So Connell Silver for sea level. Flurf, son of Nate Thompson, confirmed. Yeah, he did get a little bit of Nathan Thompson in there. I was suspicious for a minute that it was that he was a that Thompson was his Papa Flurf, but he came through from Tim Osman of the Infinite Plane Society. So I don't know, but Tim isn't into the Bible, and this guy was about to try to quote the Bible as somehow evidence, but at best it's a claim. That's all you got. Humphrey Pushcart, love that name. Once again, the Dunning-Kruger hypothesis is proven painfully. Once again, Robotham is proud. Dead, but proud. Yeah. Merrick Zions has 5 Polish PlayStation Network top. It's Polish. I don't know the N. Polish. But anyway, thank you, Merrick. Magellan says MC Toon hi from Singapore. Greetings, Magellan. Robeeb says MC Toon, consider this liability. That's from the warning. Do not drink every time he deflected. That is a guaranteed alcohol poisoning. So Heat Shield, you can thank me later for dragging Wolfie's satin-clad behind out here tonight. I'll thank you now, Heat Shield. Heat Shield commented on one of Wolfie's videos that got his attention. And then final one here, Icon Science, that says, just wanted to hit the tip jar for a really fantastic talk. Thanks, Wolfie. Thanks, Toon. Yes, thank you very much. Thank you to everybody that was along for this crazy ride. Quincy was generally a nice guy and stuck around. He did not rage quit. So, yeah. Oh, yeah. Round Thinker. This guy and Mathless Avionics Dolly can make a great team. Yeah. You don't get far in aviation without math, do you? For him to just try to like not accept math was you can't do that. And we got B Falconer's a new member. Thank you very much, B Falconer. That does remind me, the thing that goes across the bottom, I need to update that. I will get that before my next live stream. So, all right, that's the super chats. Level Earth Observer, don't be a flurf, go to school. Let's see. No demonstrable science then. Well, Leo, I don't think you quite know what science is, but we do understand that's a common problem with flat earthers. You redefine science so that you can use it to deny things that you don't like. So yeah, and Donnie, I think Donnie, who was in the Air Force and sort of worked on planes. We've also got he's been gone for a while. He was from Lake Havasu in Arizona, and he's on Facebook, and he can't not stop talking for a second. Oh, I don't miss him at all. What's his name? People help me. So yeah, Level Earth Observer, when you're ready, contact me, mc2@mc2.net. Let's set it up. So things that are demonstrable true aren't science. Well, actually they are, Leo. But you, I think, have redefined science to try to deny things that you don't like. So Lake Havasu, lake and falling down. Yeah. What? No, Lake Havasu, Arizona. Oh, help me out. He was on Facebook all the time, and he would just post memes like crazy. And it was not Roberto. No. Roberto Reeves is from Scotland. So, can't. What demonstrable science can you cite to refute? Well, nothing to refute reality, but we've measured the rotation of the Earth. We've measured the shape of the Earth. So, how about that? Yeah, and Leo, I don't think you quite have a grasp on science, because you think that a crane on a rotating Earth that is rotating at a constant rate should somehow notice and react to the constant velocity. That's not how science works. So anyway, that is what we've got. Everybody's just having fun with Leo in here. He's never been in here. I don't know if you've been here before, Leo. It's good to have you. Feel free to come back. I will be having a live stream next Tuesday at 10 p.m. UK time. That's the plan. Yes. Leo is the crane, the guy that runs a crane. He blocked me on his channel a long time ago on YouTube. So anyway, that's what I got for tonight. I am trying to get, if you watch that 5G scam in England, I've got another one on that I'm working on. So I hope to have it out by Friday at the latest. So be looking for that, because that's I think that one's pretty funny. Some new information that we found. So that's what I got, everybody. Thanks a lot. We will see you next time. Bye.